once you build a model, the next thing you can do with Heli-Dyn is you can trim the model. And trimming is for a helicopter model, especially if it's nonlinear like this one, could be quite a challenging job. So you simply go onto this on the screen and you click on this little button here. It's called Trim. So what you see in this window is first you have the initial conditions that will be used in the numeric algorithm that tries to find the equilibrium point for this helicopter. Now, as I said, since the system is highly nonlinear, the model is highly nonlinear, we have quite a sophisticated search algorithm that tries to find the equilibrium point for this helicopter. So it will find things like the positions of the controls, in this case the collective control, longitudinal, lateral and pedal controls. But it will also find the flapping angles, the longitudinal and lateral flapping angles. It will find the attitude of the helicopter, the phi and theta Euler angles, and also the main rotor and tail rotor inflow velocities. So this will be the outputs. And since this is a search algorithm, it will use these numbers as a starting point and will start searching from these points. Now, the point that we're looking at for trim is manipulated here. Heli-Dyn allows you to input two parameters for trim. One is the forward velocity and one is the altitude. So in this case, for instance, if I want to trim my model at a 0 knot forward velocity, which is obviously the trim, at 1,000 feet, the search algorithm will look for a solution at these constraints, basically the forward flight velocity and the altitude. These trim options here, they give you a bit of a freedom to adjust the performance, the search algorithm. So you can adjust the error tolerance. And as I said, the search algorithm is a sophisticated search algorithm, and it uses a lot more error tolerances than only one. So you're adjusting only one, which will automatically adjust everything else. So it will collectively reduce the error tolerance on the search algorithm. Similarly, the maximum number of iterations during the search, it might so happen that the search algorithm might get stuck at a certain local minimum, and then the search algorithm might jump from one solution to another, causing the algorithm to basically go to infinite number of iterations. In that unlikely case, we have a maximum number of iteration here in order to avoid that. All you need to do is here, after you open this, but generally we don't play with these trim options too much. They are well adjusted as they are for a regular helicopter. So if you just simply say trim, the search algorithm starts working, and you have a little cost function here. When the cost function is small enough, and that is not only the only search criteria, of course, but if it's small enough and everything else has converged, it will appear as green, and once it's green, it means that it found a trim solution, and the results are displayed here. So for this helicopter, the phi angle, the roll angle is very small. Theta is about 5 degrees. Collective is 13 degrees. This is the angle at the root of the main rotor. The longitudinal cyclic is also small, and all these other variables you simply see here. So now you can save this to a text file and you can open it later, but you can also apply this to simulation initial conditions. This is what we like to do. We like to start our simulations from this trim point. So it means all these numbers will be automatically copied to the initial conditions in the simulation tab. So my simulation will start from this trim point. So this is what I do. Now, it might so happen that you are looking for different trim conditions, not only in hover, but you're also looking at hover 10 knots, 20 knots, 30 knots, and so on and so forth. So you might want to use these calculated numbers as your new initial condition, right, for the next run. So in that case, you say apply to trim initial conditions. So if you press this button, everything on this window where you have the initial conditions for the search algorithm will be the numbers of the trim results. So this becomes again very healthy, very handy. For instance, if you want to do now a forward velocity at 10 knots, you simply will start from these initial conditions, not simply having everything 0, which will be a closer point, and hopefully the trim algorithm will converge a little faster with these new numbers. So in this case, you'll get. Let's give. So you have this again, the green here, and you have a solution here. Let me show you a case where I just tried to trim, and it blew up. Right. This was simply 20 knots forward flight. It was a good example. The search algorithm didn't really make it, so you have a red cost function here which says the trim didn't succeed. So now you can do a number of things. You can either use this, change the initial conditions of your search. This is one of the things. Another thing is you can reduce the error tolerance, and maybe you want to do that. Or, since you had a solution at 10 knots, maybe a logical thing would be to go with 15 knots first, find the trim solution for 15 knots, bring it back as initial conditions, and try the 20 knots solution using the numbers of the 15 knots trim solution. So let's try that. Maybe it's again red, so it really didn't work again. Maybe try a radically different one. Let's maybe try 40 knots and reset data so everything goes to its initial, and let's start with 40 knots. Maybe this will give us a better result, and in fact it turned out so you have a solution for the 40 knots. Now, as I said, this is a search algorithm, so the solution of the search algorithm depends a lot what your initial conditions are, on your error tolerance, and of course the flight condition. So I have to play around. Our experience is that we pretty much were able to trim the models we built on almost any forward flight velocity. So the algorithm works pretty well. Now, what's nice about this, as I said, once you have this trim algorithm and you apply it to a simulation, initial conditions, you will see these results in the initial conditions tab. So in this tab, you will see our trim solution. So what you have right now is a 40 knots forward flight trim solution. Let's do the same thing again for hover. Right, reset data, trim. So it takes sometimes a little while. So here it is. This is your trim solution. Apply to my trim initial conditions. Apply to my initial conditions, and note that these numbers will change now. They are changed to hover, to my hovering condition. So here you have it. U, V, W, the body velocities are all equal to 0. Phi, theta, psi, and all these other numbers are the initial conditions for my simulation now. Now, since this is my simulation, I can go to the simulation tab and run my simulation starting from these initial conditions. Now, if I don't like the hovering condition and I say, let's say I want to change the initial conditions to something I desire, I could actually do this. For example, I can go up here and now the aircraft is no more in trim, right? but you can still run a simulation in case you don't want to start the simulation from trim. Once you have these values, of course, you can save and load these parameters, and you can always pick up this initial flight condition for your model.